Okay, today we are going to continue from last time. So last time we start to talk about some of the applications of Bayesian asymptotics, and we see we can use Bayesian asymptotics to derive the least informative prior distribution in a parametric model given local asymptotic normality expansion assumption, and the solution to what is called Clark-Barron expansion is the Jeffreys prior. So this is the prior distribution if you don't have any, you can use if you don't have any prior information or assumption or knowledge about your problem. You can think of this as a default prior used in what is called objective Bayesian analysis. So today's topic is going to continue the discussion of applications of Bayesian asymptotics, and in particular we are going to talk about Bayesian model selection, and we will see how we can derive the famous BIC formula from Bayesian asymptotics. But before I start in this topic, let me first briefly discuss one of the homework problems, because this is the problem that I see almost everybody got it wrong. So in homework 5, question 2, it's question 3, this is a problem about biclustering. So let me remind you of the model. So the observation is a m by m matrix. So usually you can think, for example, you can think of this is the gene expression data. You have m people and m genes, and you want to simultaneously cluster the people and the genes, right? So a biclustering model assumes such a structure with both row clusters and columns clusters. So we use theta for the location parameter, sigma squared for the variance, R for the row clustering label, and C for the column clustering label. So given all these parameters, the distribution is given by theta, R sub I, C sub j, and sigma square. Okay, so for example, one special case is Ri only takes 2 values, and Cj also takes 2 values. Okay, so in this simple example, we have 2 clusters for the rows and 2 clusters for the columns as well, right? So if you look at the data matrix, okay, then it will have a checkable structure. So I organize the matrix in this way so that these rows are Ri equals 1, and these rows are Ri equals 2, right? And this is this is Ci equals 1, Ci equals 2, okay? And you have 4 parameters, theta 1, 1, theta 1, 2, theta 2, 1, theta 2, 2, right? So which means if Xij belongs to this block, then it has mean theta 1, 1, okay? But of course, in practice, you do not observe the matrix in this way. It is not always true that the first half of the rows belongs to the first cluster, right? Usually you have these labels are mixed, right? You always observe a scrambled version of this nice piecewise of this matrix of a nice piecewise constant structure. And the statistical problem is to recover these row clustering labels and the column clustering labels so that you can reorganize the matrix in such a nice way. Okay, and we can talk about EM algorithm. Let's say in general, there are k row clusters and L columns clusters. Okay. And the prior distribution for Ri is, for the row clusters, is uniform. Okay, and for the column cluster is also uniform. And the distributions for the rows and the columns are independent. Right? So let me illustrate the prior again. For example, you have R1, R2, R3 up to Rn, and here the column clustering label is C1, C2 up to Cm. Okay, so the prior means that we have these n row clustering labels and m column clustering labels. So in total, we have m plus m numbers to parameterize the clustering structure, the byte clustering structure of the matrix. And independently for each entry, you sample, for example, R1 from the uniform distribution from 1 to k, R2 also from a uniform sample from 1 to k, right? So this is for all the way to Rn, and then you independently sample C1 from 1 to L, C2 from 1 to L, right? So everything is independent, okay? Independent means that the distributions of the row cluster vector and the column cluster vector, they are independent. And the first questions ask you to derive an EM algorithm for the byte clustering problem, right? And I also ask, is the E step computable? So many of you gave the answer that E step is actually computable, but it is computationally expensive. The complexity is about the product of the row size and the column size, which is n times m. So it is expensive. This is actually not correct. The correct answer is the E step is not computationally feasible. It is not of a polynomial complexity. You need exponentially time to rigorously compute the E step. Okay, so the reason most students get it wrong is because of the factorization in deriving the E step. Okay, so when you try to figure out the E step, so many solutions try to do this. So this observation is actually correct, right? So the posterior distribution, that this is what you want to figure out, in the E step is proportional to the likelihood. Times the prior, but since the prior is uniform, so that's a constant, you don't need to write it. And for the likelihood, it can be factorized. Okay, xij given theta ri cj sigma square. Okay. So now observe this is can be factorized. So the next step is the claim that the distribution can also be factorized. Qij, okay? But this step is actually wrong. Now, why is it wrong? Well, what does this mean? This means in the posterior distribution, you can independently sample the clustering labels of all these entries, right? All these n times m entries independently. So how many degrees of freedom that you have? You have n times m degrees of freedom. However, it is obvious that the clustering structure has degrees of freedom m plus m, okay? So as long as these n numbers and these m numbers are determined, then the clustering structure of the whole matrix is determined, okay? So this factorization is not correct. It is not even correct for the prior. Even the prior distribution cannot be factorized in this way, right? So for example, if I tell you that, for example, let me just write example here. If I tell you that R1, R3, R1, C3 equals 2, 1, what does that mean? Well, this means that the first row belongs to the second cluster, and the third column belongs to the first cluster, right? So if I tell you that, and I also tell you R2, C5 equals 1, 3, right? Then it must be true that R1, C5 equals 2, 3, right? Because R1 equals 2, right? And C5 equals 3, okay? So you see that this number is clearly not independent of these two numbers. You cannot do this factorization, okay? It is true that the likelihood can be factorized, but the random variable that you are working with is of dimension m plus m. It's not of dimension n times m. Okay, so the right E step is this. It equals so you have to sum over all the possibility in brute force. Let me use a different notation, R prime I, C prime J, right? And then you sum over all possible R prime and C prime, right? So how many possibilities of R? Well, it is k to the power of n, right? How many possibility of C prime? It is L to the power of n. That's the total number of complexity you need for computing this denominator. There is no way to simplify that. Okay, and that's why in this question we have to use the variational EM algorithm to enforce the independence between the row cluster and the column cluster, right? So in the prior distribution, R and C are independent, but in posterior they are not. So variational approximation helps you to reduce the computational complexity. And I believe if you code it in the right way, the algorithm should work well in practice. Okay, so that's briefly that's all for the homework. So now let's start the lecture. Let's talk about today's topic, Bayesian model selection. So the plan is I first talk about the formula of symptotic formula of Bayesian model selection. Then I will go over some of the other methods of model selection. Some of those are frequentist methods. And finally, we can talk about lasso, which is a computationally feasible method. So in general, let's consider the setting where we observe the data x given some parameter theta. Okay, so for example, this can be a Poisson model if you want to model count data. But you do not always want to use Poisson model to model the count data. Sometimes you want to use a negative binomial distribution, right? So you may well have two models. Or in regression, you can use the Gaussian linear model to model the relation between the response and the covariate. Or you may not want to use the Gaussian linear model because you worry about the robustness property of the Gaussian linear model. You want to use a heavy tail distribution. For example, you want to model the error in the regression model by a t-distribution or a Cauchy distribution. Okay, so now the question is it possible to learn which model is appropriate from the data? Right, so in an abstract notation, I can write the setting as theta sub m and m, right? So here, I'm going to assume m is the model index and script m is a model space. So this is the model index. Right, for example, you can just use integers, m equals 1, 2, 3, 4, 5 if you have 5 models, right? And this is the model space. And each index corresponds to a different model. It can be the same family of model, for example, a Gaussian model with different dimensions, or it can be it can index completely different models, Poisson model versus negative binomial models. Doesn't matter. Okay. Now, given the model, theta m is the model parameter, right? So the parameter in the mth model, for example. Okay, and let's also assume that the parameter is in the Euclidean space. It is of dimension d sub m, right? So for different model, the dimension of the parameter is possibly different. Okay, so now the next question is how do you choose the model, right? So in a Bayesian setting, what you can do is to put a prior distribution on the model parameter. With a prior distribution, you can then compute the marginal likelihood of the model. You can then think of the model as your hyperparameter in abstract form. So we integrate out the model parameter with respect to the prior. Then we call it the density of the data given the model index. Okay? And the Bayesian model selection procedure is to use the empirical Bayes principle, which is we can maximize the marginal likelihood over the model space. Right? So this corresponds to you put a uniform prior on the model space. Of course, you can put other prior as well. It can be generalized. Now, this is a nice formula, but unfortunately, it is hard to compute. That's why we can use Bayesian asymptotics. And suppose the parametric family satisfy the local asymptotic normality expansion, then hopefully we can derive a very simple formula for such a maximization problem, which is sometimes intractable in practice. So the technique that we are going to use is called Laplace approximation. Okay, so you see here I use the word approximation, which indicates that the following derivation is not completely rigorous. So it is just an intuitive way to derive a very simple formula. And if you want to rigorously investigate the theoretical property of such a formula, you need to do it in a different way. So what is this Laplace approximation? Okay, so as an example, we can talk about how to compute the sum of exponential functions. For example, e to the power of theta x, e to the power of n times x1 plus e to the power of n times x2 all the way to n times xk. Right? So the Laplace approximation is the following approximation. You can actually approximate this sum of k terms by the largest term. Let's call it x max, right? And 1 plus little 1. Okay, so why can you do that? Well, without loss of generality, this is very simple. Without loss of generality, let's assume that the largest x is actually x1, and then you can write this sum as e to the power of n times x1, right? Then bracket, let me start another line. 1 plus e to the power of n times x2 minus x1 all the way to n times xk minus x1. Okay? Now observe that these numbers are all negative because x1 is the largest one, right? Therefore, they should be exponentially small as n goes to infinity. Okay? These terms goes to 0 very fast. Therefore, the only term that matters asymptotically will be the first term. Okay, that's the general principle of Laplace approximation. Just approximate the sum of exponential functions by the largest term. So now we are going to talk about the continuous version of Laplace approximation, which is actually more interesting. So let's study the approximation of such an integral. The integral of exponential n times a function, let's call it f theta, okay? D theta, right? So previously we deal with sum, now we deal with integral, okay? Then how do we approximate such an integral? Well, the idea is similar, but slightly more complicated. Let's first define theta hat to be the maximizer of such a function. All right, and then the idea is we are trying to approximate the integral with the largest value of f, which is f of theta hat. Okay, but of course, this is a continuous integration, right? So it is not true that you can directly approximate such an integral by the value of a function, because the measure that theta takes the value theta hat can be 0. So such approximation is not accurate. So let's actually rigorously write down the remainder. The remainder is the integral of exponential to the power of n times the difference. We just write it down. We don't want to throw it away. Okay, next, we can do Taylor expansion of this term. So this is approximately e to the power of the first term. So by the way, here I assume that theta is a one-dimensional variable. And the second term. And we are going to ignore the first term, the third term. D theta. Okay? All right, so we have the first order Taylor expansion and the second order Taylor expansion. Now, this guy is 0. This is because theta hat is the maximizer. Therefore, its derivative is 0. Okay, so we only have the second order term. Now, you can actually calculate this integral, right? Because what is in the integral is proportional to the Gaussian density function. Okay, so you can just use the Gaussian integral formula to evaluate this integral. The solution is just the normalizing constant of Gaussian distribution. Negative and second derivative of f evaluated at theta hat. Okay. Now, in order that you can actually calculate this integral and this integral does not blow up, you need to assume that the second derivative at theta hat is negative. Okay. Otherwise, the integral will be infinite. Okay, so now this formula is the Laplace approximation, right? It's very simple to derive. It's just a formula that is empirically usually works very well, but theoretically it's not rigorous, very much like what you do in physics. Okay, so now let's consider a multivariate case. Theta is now a d-dimensional vector, and then apply similar derivation. I'm going to ignore the detail. That this function, this integral is approximately e to the power of n times the maximum of f, and then times a multivariate Gaussian integral, which gives you 2 pi over n d over 2 root 1 over determinant of negative Hessian. Right? So in the multivariate case, the second derivatives can be organized into a matrix. This is called a Hessian matrix. Okay, so this is the formula that we are going to use in order to derive an asymptotic formula of this maximization problem. All right, now let's consider the following setting. Let's try to use the technique of Laplace approximation to this integral. Okay, we have a parametric model, and we have ID observation, and then we want to integrate out the parameter with respect to the prior distribution. All right, so now for this problem, we can actually write this integral as e to the power of n times f theta. Now, what is f theta? Well, f theta is the average log likelihood plus 1 over n log of the prior distribution. Okay? Now, to see why this is true, because if you multiply this f by n, then you just get the log likelihood plus the log of the prior. After you take exponential, then you get this guy, right? So now, what is the maximizer of this function? This is just the MAP. What about the second derivative? Well, let's take a look. We can take the second derivative to each of the term in the definition of f of theta. Okay, so the second term can be ignored because it is of order 1 over n. So I need a square here. It is of order 1 over n. It can be ignored. The first term, by law of large number, is going to converge to its expectation, right? And if we assume sufficient regularity condition, this is going to, by law of large number, converge to the negative Fisher information matrix. Right? So approximately the following identity is true. That is, if we evaluate the Hastings matrix of the f function at its maximizer, then this is approximately the Fisher information evaluated at the estimator as well. Okay, of course, if you want to prove that, you have to assume that the Hastings is continuous with respect to its parameter, and the theta hat is also consistent. Okay, so now we can apply the Laplace approximation formula. Okay, let's take a look at the formula again. For such an integral, we can approximate by this formula. Okay, so in this formula, we only need to figure out what is this guy, right? And we just figure out this guy. This is the Fisher information. So after application of Laplace approximation, this marginal likelihood is approximately, well, the first term is going to be the function that you are going to integrate out, evaluated at theta hat, the maximizer, right? So it will be pi of theta hat, and then the likelihood function evaluated at theta hat. Okay, so what's the next term? The next term is this factor, 2 pi over n to the power of dimension over 2, right? And then finally, we have root 1 over the determinant of Fisher information. Okay? All right, so we obtain this formula. This is simpler than the original integration because we don't need to do integral anymore. However, this is still a little bit complicated. First, because we have the prior, right? We need to calculate the prior distribution, the prior density, the value of the prior density at theta equals theta hat. And we also need to calculate the Fisher formation. Okay? What if we don't need to calculate that? That would be good, right? So, well, it turns out there is such a choice, right? Such a choice is choose Jeffreys prior. Okay? What is Jeffreys prior? Well, Jeffreys prior is pi theta proportional to root determinant of Fisher formation matrix. Okay? So if you choose Jeffreys prior, these two terms will be cancelled out. Right? So when we choose Jeffreys prior, two good things happen. The first one is this guy becomes a constant. Okay? Now, the second property, which is actually a new property, I haven't said it before, is that if you choose Jeffreys prior, then theta hat, in this case, that is the MAP, it's going to be very, very close to the maximum likelihood estimator. Okay? And in fact, for any prior distribution, the first order expansion of MAP and MLE are the same because we have already know that both MAP and MLE are going to converge to the same asymptotic normal distribution, normal zero inverse Fisher formation, right? So the first order approximation will be the same regardless of the prior distribution. The reason is that the contribution of the prior is second order. However, in addition, if you choose Jeffreys prior, not only they have the first order, they have the identical first order expansion, the second order expansion of these two estimators are also the same. Okay? So when you choose the Jeffreys prior, the MAP and the MLE, they are particularly close. They are very, very close. You have to go to the third order term to figure out the difference. Okay? That in fact, if you pose a question, the question is which prior makes the MAP as close as possible to the MLE? Well, the answer will be the Jeffreys prior. Okay? So with these two good property, and then we can have the following formula. This integral is approximately proportional to 2 pi over n to the power of d over 2 times the likelihood function, and we can replace theta hat by the maximum likelihood estimator. Right? Now let's go back to the original formula that we are trying to maximize. This is the formula that we are trying to maximize. Right? So with the approximation, the maximization problem is approximately log minus dm over 2 log n over 2 pi. All right, so we have this problem. Okay, so this is what we have derived. And in practice, what people usually do is to further ignore this 2 pi, right? Because log of n over 2 pi is log n minus log 2 pi. Log n goes to infinity. Log 2 pi is a constant. It can be ignored. And therefore, we have arrived at the BIC formula. This is the one without 2 pi. Okay. So originally, we want to do this maximization. The difficulty is here we have to do this integral. If it is a conjugate prior, then it is feasible. Otherwise, you cannot really do it. Now, using Laplace approximation for a general smooth parametric model, such a maximization problem can be approximated by this formula. Right? This formula is very simple. So here's the idea. For each model, you first compute the maximum likelihood estimator, right, by maximize the likelihood function. And then you are going to compare different model by the likelihood function at its maximum, penalized by the dimension of the model. Okay? So the larger the dimension, the more penalty the model will receive. So BIC always prefers simpler models, right? This is very intuitive. For example, if there are two models that model the data equivalently well, of course, you want to choose the simpler model, because the simpler model, when you estimate the parameter, it will have a smaller variance, which means for future data that you haven't seen yet, a smaller model is better in terms of generalization. Okay? Without this term, you will always prefer a more complicated model. Therefore, you will eventually overfit the data. Okay? So a penalty such as this is actually necessary. Now, what people usually do is to apply the BIC to a regression problem. Let's then take a look at what formula we are going to get. So in a regression, we have the Gaussian likelihood function. This is the Gaussian linear model. Y is distributed by a design matrix X of size n by p times the regression vector of size p. Right? The variance, the covariance matrix, sigma squared times identity. Okay, then the likelihood function of this problem is proportional to e to the power of negative 1 over 2 sigma squared y minus x beta L2 norm squared. Now the BIC formula for this problem is to you do the least square first, right? And the BIC score is you are going to add a penalty, which is sigma squared times dimension times log n. Okay? So this is the BIC score, right? So it is equivalent as the more general setting, where I changed the maximization into minimization by looking at the negative log likelihood function. So in linear regression, there is actually another popular model selection formula. This is called AIC. It's very similar to BIC. Again, you first do the least square and then add a penalty. But the penalty has a different formula. It is 2 sigma square times p. Okay. So in general, if the sample size n is very large, and then BIC will tend to give you a sparser model because usually log n can be greater than 2. Okay, but how do you derive AIC? So actually, we have, in some sense, have already learned AIC. So let me try to convince you why this is true. Now, I want to tell you something about Shor. So this is called Stein's unbiased risk estimate. Okay, so the reason I said we have already learned that is because we have implicitly used the idea of Shor in the proof of James Stein. In the proof of James Stein estimator dominates MLE. When we analyze the risk function of the James Stein estimator, we use Stein's identity to deal with the inner product term. Okay. And so that we can rigorously analyze the risk. Now, it turns out the same idea can also give you a unbiased risk estimator, and we can use that to derive the formula of AIC. Okay, so let's, in general, consider a Gaussian model, because remember, the Stein formula requires the exact Gaussian distribution to use. Now we consider a n-dimensional multivariate Gaussian distribution, and which generates data y. Now let's consider an estimator. Mu hat is a function of the data that estimates mu. Right? We can look at the risk function. Right? So the risk function characterizes how accurate the estimator mu to the truth. Now, since the risk function involves this expectation, and the expectation is induced by the distribution with the true mu, so in general, you do not know the risk. Okay, so if you have data, of course you can calculate the estimator, you can estimate the parameter, but you do not know how well you are doing. You may be very accurate, but you will never know whether you are actually accurate or not. Okay, now the Stein's unbiased risk estimator, the idea is try to estimate this quantity. Okay, so this quantity depends on the estimator. It also depends on the truth because it has mu here and also mu here, right? So if we can find an estimator to estimate this guy, then we can know, we will know how well we are actually doing in terms of estimation. So to derive this estimator, here's the trick. We can write the difference between mu hat and mu by mu hat minus y plus y minus mu. And then we can expand it. Mu hat minus y. This is the first term. We also have the second term. And the cross product term. Now the first term is already okay, right? Because how do we estimate this guy? Well, without expectation, everything can be calculated. Therefore, the L2 norm squared between mu hat minus y is going to be an unbiased estimator of this quantity, right? Because expectation is this quantity, right? And the second term is also okay because y minus mu is going to be a standard Gaussian. So this guy is n times sigma squared. Now, what makes the trouble is the cross product term. Let's actually split the cross product term further into two terms, which is the inner product between y hat and y minus mu, mu hat and y minus mu, and y and y minus mu. Okay? So what is this guy? Well, for simplicity, let's define z as y minus mu. Then it is normal 0 sigma square identity. Okay? So we can actually replace y minus mu by z and y by mu plus z. Now this is the inner product between mu and z and itself, right? So the inner product between mu and z is 0 because the expectation of z is 0. So the only thing left is the L2 norm squared of z, which is n times sigma squared, right? So n times sigma squared minus 2 times n times sigma squared. So the answer will be minus n sigma squared, and then plus the inner product term. Now we have z here. Okay, so here is the place that we can use Stein's identity. Right, this is actually in the analysis of the Jamestown estimator, we use the same argument. We can write this guy by Stein's identity. If you forget, you need to take a look at the formula again. Plus 2 okay, so here I made a mistake. I should actually call let me actually write y minus mu by sigma times z. Okay, so this is a better notation because then z just follows a standard Gaussian distribution. All right, so therefore I should replace the z here by sigma times z. Right, so it's always better to use z as a standard Gaussian vector. Okay, so now everything is good. Let's do it again. Plus 2 sigma, and then expected value of sum of the partial derivative. Okay, so mu is a n-dimensional vector. So mu hat I is the ith entry of mu hat. So now we are going to replace the partial derivative with respect to z with respect to y. Okay, then we also need to correct it by the derivative between y and z. So what's the derivative? What's the partial derivative of y with respect to z? Well, here's the formula, right? So y equals mu plus sigma z. Okay, therefore the partial derivative is going to contribute to another sigma. Minus n sigma squared plus 2 sigma squared expected value of sum of the partial derivative. All right, so here we can define Stein's unbiased risk estimate of mu hat as the L2 norm squared between mu hat and y minus n sigma squared plus 2 sigma squared sum of the partial derivatives. So let's write down a theorem. Right, the theorem says the expectation of sure is the risk function. How to prove it? Well, this is the proof. Okay, so now let's take a look at the formula of Stein's unbiased risk estimate. We see that every term can be computable, right? So mu hat is an estimator. Of course, you can compute it. Y is the original data, right? So you can compute it. You need to assume you know sigma square. So if you know sigma square, n times sigma square, you also know it. For the partial derivative, since the estimator is a function of y, right? You know this function, so you can also calculate the partial derivative. So in fact, this term, which is the sum of the partial derivative, has a name. This is called the degree of freedoms, the degrees of freedom of the estimator mu hat. Okay, the reason it is called degree of freedom is usually for many situations, you can actually show this term actually equals the dimension of the parameter mu. Okay, for example, let's play with the linear model. Right, so in linear model, we have a multivariate Gaussian distribution with mean x beta and covariance sigma square identity, right? So what is our mu hat? So first of all, this is our mu. Our mu hat is the least square estimator, right? So it is h times y, where h is the hat matrix. That's the projection matrix onto the column space of x. So here we assume that x is full rank. You can work out the situation if x is not full rank. But projection matrix is still well defined. Okay? And then we can evaluate Stein's unbiased risk estimate. Right? So the first term is just the y minus x beta hat. Right? The second term is n times sigma squared. It's not interesting. What is interesting is the third term, so we need to calculate that. Okay, so what is the partial derivative? Well, here's a formula, right? Mu hat equals h times y. This is a linear function. So for the ith coordinate, the partial derivative with respect to y is the entry of the hat matrix on the diagonal. So it's HII. Okay? So this is the trace of H, which turns out to be the dimension, right? So if X is low rank, then you calculate the trace. This will give you the rank of X. Okay? So still the dimension, right? So the Stein's risk unbiased estimator of X beta hat, that's your least square estimator, is this guy minus n sigma squared plus 2 sigma squared p. Okay? And if you look at the formula, right, the first term and the third term changes with the model, because if you use a different model of different dimension, then the estimator change, the dimension change. The second term will not be changed because that's always going to be the sample size times the variance. Okay, so when you apply to the linear model, actually, when you compare different models, the second term is not important. That's why, in this case, we have derived AIC. So what is AIC? Well, for AIC, you want to minimize. You want to first find the least square solution, right? And then you penalize the likelihood by 2 sigma square p, right? This is the AIC formula that we just wrote previously. And you can see we have derived AIC from Stein unbiased risk estimate. The reason we have a different name, AIC, for this formula is because AIC was originally derived in the context of time series analysis from a different perspective, minimize the callback liability between the true model, the true data generating process and the model. And here, for the linear model, it is the same as Stein's unbiased risk estimate. That's why we can have another clean derivation. Now, the reason this is called AIC is because people believe A stands for archaic. This is the Japanese statistician who first derived the formula of AIC and the corresponding model selection formula. However, according to archaic himself, he told other people the reason that he called this method AIC is not because this is archaic information criterion. He called AIC is because it is an information criteria. Okay, so basically he claimed he is a very humble person. He doesn't want to name the method after his own name. It's just this N. But of course, this is not what it says in Wikipedia, right? So it doesn't matter. All right, so we have AIC and we have BIC. So for linear regression, the most general form of model selection is called all subset selection. So what's the idea? Well, the idea is we just rewrite the formula of AIC and BIC in terms of subset selection, in the sense that when we specify the Gaussian linear model with mean x beta and covariance sigma square identity, here, what we specify here is the full model. Now the question is, if we assume the true beta is sparse, in the sense that beta j equals 0 for many coordinates, right? Then can we find the best model? For some subset of P, okay? So here I use this notation for the integer set 1 to P, right? So here's the setting. We have a full model, but we know that many of the beta are 0. For example, if we do regression in genetic analysis for gene expression data, then usually people assume the phenotype only depends on a few genes. Okay, so you expect many of the coefficients should be 0 or at least very, very close to 0. Right? This is called sparse linear regression. So how can we find the best submodel from the data? Okay, and one of the method is L0 penalty. So the definition of L0 penalty, or the L0 norm of a regression coefficient, is the number of the non-zero coordinates. Right. So if L0 penalty, if L0 norm is 1, that means beta only has one non-zero entry. If the L0 norm is P, then it is a dense vector. Okay, so the method is when you do least square, not only do you minimize the square error, you actually minimize the sum of the square error plus lambda times the L0 norm, right? So this is the penalty of the complexity of the model. Okay, so this is a very intuitive idea. As I just said, if you don't add this term, you will always favor a more complicated model. Okay, if you just use the first term to select all model, you will always end up with the full model that S equals the whole set, right? Because if you use a larger model, the residual is going to be smaller by some simple derivation. So you have to add some penalty. So one popular choice is the dimension of the model, which is the number of non-zero in the regression coefficient. Now, it turns out both AIC and BIC are special cases of the L0 penalty model. Okay, so in order to see that, let's rewrite this optimization problem as we can actually first minimize over the sparsity, which is the number of non-zero S. Okay, and then given S, we can minimize over the subset, right? We can find the best subset such that the cardinality equals small s. And then we can restrict ourselves onto the submodel. So the notation X sub S means a design matrix of size n by small s, where the columns are from the subset S, right? You throw away other columns, just keep all the columns in the subset. And this notation means you throw away other coordinates in the complement set of the S, right? You just use the subvector and plus lambda times S. Okay, so why AIC and BIC are special cases? Well, because AIC and BIC, they just correspond to different lambdas, right? So what is the lambda of AIC? Well, for lambda of AIC is 2 sigma square, right? What about BIC? It's sigma square times log n. Okay, so if you choose these two penalties, lambdas, the procedure of corresponding subset selection are going to be exactly the AIC and the BIC procedure. Okay, so now what is wrong with this procedure? Now, first of all, these two choices are not going to give you the minimax rates of sparse linear regression. They're actually a better form of penalty that we can use in terms that leads to better risk behavior. Okay, and second, you see that L0 penalty is equivalent to first solve the least square problem, right? So sorry, here I made a mistake. Here should be minimized over beta s. Okay. So as you can see, the L0 penalty problem, you first solve this least square problem on the support of S, right? So this is doable. This is just the ordinary least square solution. However, you need to do that for all subsets with different cardinality. So in the end, you can only do that with exhaustive search. The number of subsets is 2 to the power of p, right? You need to go over all possible subsets, and for each one, you compute the penalty level, which is easy, and compute the least square as the least square score of the problem. So there are exponentially many possibilities. So this is not computationally feasible in practice. So in the next lecture, we are going to talk about a better form of penalty, and we are also going to talk about a penalty in particular that is computationally feasible. This is the Lasso estimator that is very popular in high-dimensional linear regression. So see you next time.